See,
That's
okay,
great.
okay, now I can stumble here. Okay, it's talking about star formation histories. Yeah, please go ahead.
All right. Thank you so much. And it really is an absolute pleasure to be here and see everyone in person after so long. I still don't have my sea legs for giving in-person talks instead of on Zoom, so if I stare off into the middle distance. Um, I have a really tough act to follow after Linda and David, so I'm going to do a Monty Python and say, and now for something completely different, and talk more about techniques and essentially how we as people who do analysis on observations and theory can sort of keep up in sort of getting the most out of the data that we work with, right? And in particular, how this relates to star formation histories. So before I go on, none of this work that I'm going to talk about today would be possible without a large and extremely supportive network of collaborators. So I do want to thank all of them. And also for all the people who write incredible open source software that we all use in our analysis, right? It's a really big part of what we do. All right. I don't know how that got there. All right, so the way this talk is going to work is I'm going to talk about why star formation histories are interesting and how they relate to the timescales that are important in understanding galaxy evolution, how we can get at them with observations in this using this non-parametric way, how we can compare those to what we have in cosmological simulations, what we learn, and then what we need to constrain to sort of learn more, and then how we can bridge that gap by modeling star formation rate covariances and what that means. And finally, I'm just going to briefly plug this thing called the Pan Survey SED forum that we have been running for the last few months. Okay, so let's jump in. The main question a lot of us are interested in over here is what causes the diversity that we see in galaxy populations, right? This is the elephant versus squirrel analogy that David put forward. And I would say that there's a whole bunch of answers depending on who you ask. And the interesting question to me is sort of figuring out which of these processes go into elephant formation and evolution versus squirrel formation and evolution. And the reason this is so hard to study is because there's a whole bunch of different timescales that these processes act on. And not only do they act on different timescales, they overlap, they're not well constrained, and there's a lot of interactions between these terms, right? So that makes this a very hard but very interesting problem. And so the question that I'm interested in is sort of how do we quantify the effect of these different processes on galaxies on these different timescales and then characterize them and figure out what their relative strengths are at a given epoch. And so briefly, like there's all of these shorter, relatively speaking, timescale processes that influence GMC creation and destruction and structure formation in galaxies that persists only on a few dynamical timescales, to long timescale processes that are related to the growth of their parent dark matter halos and baryon cycling and things like that. So there's a number of ways of measuring timescales, and I'm not an expert in all of them. Doubtless there are people in this room who have their own ideas of how to go about this problem. And so there's ways we can measure it directly and indirectly, and I'm going to talk about star formation histories which sort of encode the effects of many different physical processes on different timescales and talk about how we can measure that, what we can learn from them. So this is a star formation history, right? It's a star formation rate as a function of time going all the way back from the Big Bang to the time of observation of a galaxy. And there's a lot of structure here sort of on the long time scales and on the short time scales that presumably comes from the physics of whatever is going on in this galaxy. And why we study star formation histories? Again, because I said they contain information about these physical processes. And like here I'm showing a very brief example where you have 3 star formation histories from a list of TNG, and there's this correlation between how they look, like what their morphology and structure is on large scales and what their overall star formation behavior is over time. And the way I'm going to set up this problem is from two different viewpoints. One is that we have observations and we want to do some kind of inference on them to get at star formation history information. And the second is we have models and simulations that come from theory, like both analytical models and cosmological and zoom-in simulations. And from there, we want to do some kind of time series analysis to sort of back out the connection between the physics and the observer, the star formation history. So this is sort of like acting as an in-between platform to connect these two. And so this is the bridging the gap, sort of. Okay. And there's a whole bunch of science that you can do with star formation histories, and I don't think I'll have time to go into all of them. I've put up a list here, and I'll share the slides. And there's some that can be done that sort of focuses on the longer timescale aspects of it, and some that focuses on shorter timescale variability in star formation rates, or burstiness, as it's sometimes called. But talk to me about this afterwards if anything interests you. Sorry. Keeps getting back. Okay. All right. How do we get star formation history information, and why does it matter how, right? Like for the longest time when our data wasn't good enough, we used to treat the star formation history as a nuisance parameter that we marginalize over to get at derived quantities like masses and star formation rates, right? And sorry, there seems to be a lag. Okay, and a lot of like the science that we do in terms of mass functions and scaling relations and so on depends on these masses and star formation rates that we estimate. And if there are systematic factors in biases sort of that come into our estimates of these properties as a result of what we assume about the star formation history, then that's going to affect all the downstream science. So the question is, how do we model individual star formation histories, and why does that matter? Briefly, right, we usually work in flux versus wavelength space. In the space, we have some combination of spectroscopy and or photometry. The spectroscopy provides detailed features. The photometry provides a wide wavelength baseline. And we fit this with some inference mechanism to get a posterior in SED space. And this posterior corresponds to posteriors in all the physical parameters that sort of go into our model for how these parameters affect a galaxy spectrum. And in particular, whatever model we assume to describe the star formation history, the posteriors in that sort of give us a shape in star formation history space that we can then learn from. And so there's a whole bunch of different ways in which, oh, maybe I should do this. That makes a lot more sense. Okay. So there's a whole bunch of different ways in which people talk about star formation histories. There's a traditional class of parametric forms that include tau models and delayed tau and double power law and so on. But there's also these sort of non-parametric ways. One that's commonly known is to sort of divide time into bins and let the star formation rate in each bin be a free parameter. Another way is to just take a bunch of star formation histories from a simulation and use that as something to evaluate likelihoods. And a third is this Gaussian process-based stuff that seems weird, and I'm going to talk about that a bit more. And the reason this matters is because there, at this point, have been multiple studies that show that how you do star formation histories can strongly influence systematic biases in stellar masses, right? At the very basic level, the quantity that we consider most robust can still have factors of 0.2 to 0.3 dex systematic differences based on what star formation history parameterization you use. So it's really important to pin this down so that everything else is robust. Okay. Now, what is this Gaussian process-based thing? It's called the dense basis method. And the way it works is, instead of working in SFR versus time space, you work in cumulative SFR versus time space, so the integral of the star formation rate. And because everything's normalized, it goes from 0, 0 to 1, 1. And so a line connecting that would correspond to the, like the star formation history would be the derivative of that line, which is a constant SFR versus across time. If you put in a single point as a constraint, in this case T50, the time when the galaxy formed half of its mass, and you draw a line that goes through that T50, and then you take the derivative of that. Now that gives you a star formation history with some shape. So putting in these Tx parameters, the times at which a galaxy formed certain fractions of its mass, gives you constraints on the shape of the star formation history. And if you have uncertainties on this T50, then that will also translate to corresponding uncertainties on the star formation history shape. And so the more of these Tx parameters you have, the better you can constrain the overall shape of your star formation history, and you're not assuming anything about a priori what the parametric form of this curve is. And the way you draw those lines with uncertainties is using these things called Gaussian processes that I'll come back to in a bit. So the nice thing about this kind of formalism is just with that one T50 parameter, right, you can have a variety of star formation history shapes. You can have things that are rising, that have high SFR and short T50. You can have things that are recently quenched with low SFR and short T50. You can have things that are rejuvenated with large T50 and high SFR, and recently versus quenched a long time ago population. So all of this is with just two parameters, SFR and T50. And if you have more parameters, then you can sort of go in more detail and sort of constrain the shapes of the star formation histories regardless of how complex they are, right? And this sort of breaks a common notion about non-parametric star formation histories that people have, which is that they need a lot of free parameters, right? You don't. Instead of trying to think of SFR in each bin as a free parameter, you can now just think of, say, just the T50, the time when it formed half of its mass, as your one free parameter and still get a lot of flexibility out of it, right? So this is sort of my answer to the first point, which is that a lot of our theories are built on masses and SFRs, but by modeling star formation histories carefully, there are ways where we can estimate these properties more robustly. And we've done a whole bunch of validation tests that I'm happy to talk about that sort of test whether the recovery of star formation histories using this method is robust or not. Right? This package is available. The code is like out there. If you want to use it, come talk to me. I'm happy to help. Now, the things we can do with this, some of them. One is applying this to candles. We can sort of get the star formation histories of all the galaxies across a range of stellar masses and redshifts. And so this is going from redshift of 3 to 0.5 and stellar masses of 10 to the 9 to 10 to the 11 and a half. And the different curves show the 5 different candles fields. And you can see that without sort of assuming any parametric form, you can sort of get the evolution of star formation histories across time, right? And I really like this plot, but when I talk to people, they're like, yeah, but give me some summary statistics so that I can talk about evolution of quantities. And so two sort of applications based on this data set are one that you can now link populations across time in a longitudinal sense instead of just looking at cross sections at different epochs. And you can sort of trace galaxies as they move along different spaces as they evolve. The other thing you can do is couple this with ancillary properties like morphology and start looking for correlations between the star formation histories and these other properties. I'm going to quickly plug incredible stuff that some of my students are doing, which is looking at the signatures of AGN feedback in when galaxy is quenched in the SDSS manga sample using signatures in the star formation histories, or teaching a neural network to predict star formation histories just from galaxy images and then going back and asking the question, what did the neural network learn? Which part of the image does it use to make its predictions? And Kate Gould at Dawn is working on a sort of bespoke atlas of star formation history priors to try to figure out when the first galaxies in that sample quenched for the Cosmos 2020 sample. So feel free to reach out to them or ask me, and I'm happy to tell you more. Okay, another quick thing that I couldn't resist putting in was when we were looking at early web data, we noticed this object that got triply lensed, and one of those objects got magnified by a factor somewhere between 10 to 100 and has a caustic passing through it. And so we started looking at this object and we noticed all of these tiny dots around it, right? Bob Abraham started calling it the sparkly sparkler and the name stuck. And when we saw them, we sort of did some basic analysis to see whether they were compact, whether they were associated with this object or foreground contaminants, and you can see them across multiple images that we matched. And finally, whether they were quenched or star forming. And so when we just looked at their colors, the colors were red, right? So we were like, okay, we need to see if we can determine when they formed. And I have so much more respect for aperture photometry in crowded fields now than I ever did before. But the nice thing about the dense basis in this context was that when we could not remove the foreground contamination from the host galaxy in our early photometry, our SSP fits for these objects were completely failing, but the dense basis fits were sort of able to show you two stellar populations distinctly, one young and one old. And the young one corresponded to the host galaxy, and then with better photometry, we sort of converged to a point where we were able to remove that background, and now you're only left with the old stellar populations for these things. So this was really cool to work on and sort of shows what a non-parametric method can do. All right, switching tracks, right? How do star formation histories in cosmological simulations look like? Well, overall, they have the sort of same trends. But when you, because they are so much more information rich, when you go to Fourier space and look at the time scales in the power spectral density space, you notice, again, overall trends in terms of what their shapes are. And these trends are set to some extent by the accretion histories of the dark matter halos. But you also notice differences both with mass and across simulations that come from both numerical but also physical models that are put into these. And so if we sort of take slices in this power spectral density space, right? So at any point, right, you can plot the slope of the PSD, which is related to how energy is sort of transferring from one scale to another, or how SFR fluctuations at adjacent timescales are linked to each other. And you can plot the normalization, which is the overall strength of these fluctuations. And you see these sort of nice trends with increasing stellar mass, and you can, based on that, look at a certain timescale and say, okay, I know that this is the physics that's happening on this timescale. Now this is how it's influencing SFR variability at a given mass. This is great. I can learn so much. But if you now generalize this to all the simulations, it's all over the place, right? It's been really hard to sort of get observational constraints in this space. And as a result, like, the simulations sort of treat this as, well, this is just unexplored territory that we have, right? And so constraints, if we can get them observationally in this space, would be amazing, right? In terms of constraining the strength of the different processes that are regulating SFR variability as a function of timescale. And so that sort of sets up the problem that I'm attempting to solve. I'm nowhere close to the solution, right? But this is what I want to do. So it's difficult to connect physics to observables. But if we can get constraints in power spectral density or some analogous space, then it might be possible to do using this approach. And so the way I do this is, let's go back to how we were talking about star formation histories. We model them as Gaussian processes. A Gaussian process is made up of two things. It's a stochastic process that has a mean and a covariance. What this means is that at any point in time, if you have some quantity of interest, in this case SFR, you can define a mean function, which is the long time scale behavior that I've been showing with the dense basis fits. And you can also define a covariance matrix that I've been sort of marginalizing over in my previous case, but now you can actually come back and talk about this covariance. And the colored curves show you sort of individual samples from this mean and covariance model. And so what that means is, when you have some kind of observational constraints, you can condition the covariance matrix and the mean on the observational data to get something that looks like that, right? So that's the Gaussian process conditioned on the observations. And now you have constraints on, like, the attributes of both the long time scale mean behavior and the shorter time scale covariance behavior. And so this is stuff that I've been working on with Josh Spiegel. We basically took Sandra Takela, John Forbes, and Nevin Kapla's model of the extended regulator PSD, which has 3 timescales in it. A timescale for stochastic gas inflow, one for equilibrium within the gas reservoir of a galaxy, and for GMC creation and destruction and all the processes associated with that, right? So it's an effective timescale model, right? I'm not saying that this is the timescale of gas inflow. This is the effective timescale when you factor in gas inflows and outflows and all the other things that sort of change the overall gas reservoir. And what we can do is, the Wiener-Khinchin theorem allows us to take this thing in Fourier space and reformulate it in regular time as an autocovariance function, right? So this is how star formation rates at 2 times are correlated with each other. And now this autocovariance function has the same timescales that were in the model, but now the autocovariance function is something that neatly fits inside the GP as my covariance matrix that I showed earlier. And so now you can draw samples from the Gaussian process that has this very physical covariance structure. And then you can run that forward through FSPS and generate spectra and therefore all the observables that we know and love, right? So this is coming all the way back to observable space. And so you can see how each of the sort of physical parameters that we care about depend on the extended regulator model input parameters. So like the strengths of the dynamical component of that model, the GMC component of that model, and the timescales. And you can go ahead and you can sort of create mock populations of galaxies. So here we made sort of 4 mock populations that are Milky Way analogs, dwarfs, cosmic known massive galaxies, and high redshift galaxies. And we sort of forward modeled what distributions of their observables might be, right? And so again, it's to sort of bring this back, it's difficult to connect physics to observables, but doing this sort of process where we take physically motivated covariance functions that correspond directly to part of the physics, we can create parametric models in covariance space that let us constrain these timescales. And preliminary stuff with SDSS observables actually makes it look like we can constrain these observationally. Okay, last thing. There's a lot of incredible data coming out, not only now with Webb, but also with future observatories. And we created this thing called the Pan-Survey SAD Forum as a place for people to talk about what the state of the art is in many different things, whether it's redshifts or star formation histories or dust. So what we want to do is both bring in experts to sort of talk about these different things and tell us what the best techniques are, what the bad assumptions are, and also to sort of provide a space for people to discuss, right, and encourage cooperation among different groups. So the link to the website is up there. You can join our Slack workspace if you want to. And we are sort of putting together an event for grad students. So if you are a grad student or if you have a grad student that you'd like to nominate, please do so, and you can sign up here or on the website. And yeah, I'll leave my conclusions up, and I'm like, there are so many expansions and possible questions you can get at with this formalism. If there's anything you want to talk about, please come find me. Thank you. Thank you so much.
Okay, thank you, Kartheik. We have a couple of questions.
I love this stuff.
Okay.
You glossed over what I call the connect the dots problem, which is basically trying to trace through a galaxy history through time by connecting what we observe at different epochs. Could you go through that a little bit more?
Yeah, absolutely. So I guess this might be all the way back at the start, but let's see. So this sort of thing, right, where so basically from the observations we can have some set of spectral observables. This could be photometry, spectroscopy, or a combination. That's what my model is currently set up to deal with, but there's no reason we can't fold in additional things like chemical abundances or depletion times as we sort of make a coherent picture for them. The star formation histories are really interesting because they are a test bed for all sorts of variability that both our spectral features are sensitive to on different timescales, but also sort of encode the long timescale evolution that comes from halo scale processes. On the model side, right, there's all of these different simulations where they try to put in all the physics that we think happens in galaxies. There's things like resolution limits and other things to be careful about. But what you can do is you can either compare across simulations, or as Yunjin was showing yesterday, you can perturb the model within a single simulation and see what happens to the power spectrum, what happens to the star formation histories when I change a kind of feedback, when I change the bulge to total ratio, or models like the small boxes in Illustris TNG where you can go in and you can turn winds off, you can turn on and off AGN feedback and so on and see what happens. And so because the star formation history is sort of this common object that has signals from all of these things, I think it's a great way to sort of bridge these two very different sets of data and analyze it on a common space. I don't know if that answered the question or. Yeah.
It's beautiful work, of course. This is how data should be analyzed these days. It makes me feel a little old when I fit a power law to a bunch of data points. But you're, for example, here with the star formation histories, right? You assume an underlying ground truth in the star population model. Yet there's like 6 defensible choices for the isochrones. There's at least 3 defensible choices for the stellar template spectra that go in there, and not just dust, you know. So how do you test the uncertainties associated with those choices? You can devise these complex exercises of generating the mock spectra from a simulation with one set of choices, then fit them with another and see how things... Are you exploring that? Have you gained any insights into this problem? Because that's what we're running into with legacy now. Right, we have very advanced methods that others have devised, like Joel, to analyze our spectra, and they all give beautiful answers that are all completely different.
Okay, that's an amazing question and keeps me awake more nights than I care to say here. There's 4 answers that I could go into, and we can do part of this offline because that's an entire talk in its own, and it's an amazing talk to sort of do. Briefly, right? One is compare between different models. Cami Pachavici has this sort of ongoing paper that she's working on where we fit the same sample of galaxies with 14 different methods, different SED fitting codes with different assumptions, and sort of quantify the systemic scatter as a result of different modeling assumptions. So there you have, as a function of stellar mass, star formation rate, dust, the inter-code scatter that comes in because of different modeling assumptions, and that sort of gives us a rough estimate of what the systematics are for a given kind of data. So that's one. And we have an HST grant that's sort of set up to compare 4 different star formation history codes across all of candles. So that's also going to be useful for this exercise because one of them's, like you mentioned, prospector is going to be one of them, dense space is going to be another. And so we have these different non-parametric codes that will get compared. The second is posterior predictive checks, where you leave out part of your data and you then try to predict it with your fits, right? And can you get FIR fluxes right? Can you get other things that you know are not directly informed by the data right with your model? So that's number 2. Number 3 is self-consistency checks, and I think Sandy is a big fan of these, where if you have the SFR M-star correlation at a low redshift, can you sort of, with your star formation history, self-consistently recover that at higher redshifts? If you have the mass function at low redshift, can you self-consistently, using star formation histories, recover that at higher redshifts, and so on? So that's number 3. And number 4 is what you mentioned, where you generate mock data with simulations and then fit them with different assumptions to sort of see, with respect to like the ground truth in the simulations, how do you go wrong, where do you go wrong? And sort of, I have a quick plot to show for that last one because that's sort of a standard test that we do. This is super small, sorry. But like this is for a sample of 10,000 star formation histories, this is sort of like our ensemble accuracy as we go back and look back time. Right?
Okay,
And
so I think let's break here.
Yeah,
In the interest
sorry
of
for the
time,
long answer.
Please direct your further questions to Kartheik over the coffee break. I think that's a good opportunity. And let's meet here at 11:30. Okay, so 5 minutes so later. And let's thank Kartheik again.
Thank you. It was super nice to talk here.